Audio win. Oh, it's good. All right, I don't know what happened there. I've set this up, I don't know how many times, but that time it just decided it was going to take a little bit longer. After checking if I could connect the mic 5 different times without doing anything other than checking, it actually worked. So, organize my screen just a little bit and I am ready to go. Haven't checked over on the YouTube. I have confidence that this is working though. That's good. We got something going. I see somebody said I'm good. Yes. Haha. All right. Okay. Let me get to the broadcast and presentation. Okay. Today we're talking about some algorithm families. There's 6 of them that we're going to discuss. We kind of pull them together in pairs. And what an algorithm family is a general approach to how you actually write an algorithm for a particular solution. So we'll be looking at some of them, and we kind of do them in pairs because they're somewhat related, and then we'll make some sense out of them. The easy ones you'll sort of get, or we'll kind of have done already, and we'll just give a little bit of formal discussion of what it is, then we can move on. The more complicated ones that we're going to talk about, we will have separate lectures for them following this. So today we're just going to talk about the families here. We're going to talk about brute force and greedy. Those are something that we'll give a good solid definition to and then move on from. Divide and conquer as well is something that we fundamentally understand. And the last 3 here, those are the ones that are more complicated. In DP, dynamic programming, that's always a staff favorite. There will be a dynamic programming problem on the final. So make sure you get a chance to understand this a bit. Do some online research, do some office hours, question asking if DP is still escaping you. There's a lab 10 that's going to be working on DP, and DP is a notoriously hard concept it's an easy enough concept, I should say. It's often hard to implement. So that makes it a bit of a high stakes problem on the final. You do have some partial credit that you can get by working your way through the mechanics of making a DP solution. Do the things that you know you need to do, even if you don't quite understand what the actual answer in the end is. You're going to get enough of the setup there to get some points, and often getting the setup in place really, as you try to write the whole solution ahead of time, is a lot more difficult than if you just get some of the setup in place and it gets down to like, well, what do I need for this right here? I've got all the other things set up. It's the part that I don't, it's really easy. I just need the biggest one of these 2 or 3 options. Let's take that, and then that finishes it. So DP is something that you'll have to work on. My suggestion is now, go to one of the coding sites. Look at their DP tutorial. Start looking at some of their DP solutions. You don't have to do a whole bunch of them, but a lot of our DP problems end up being another version of a different DP problem. So if you see quite a few DP solutions between now and the final, you're going to be a lot better off. Even if you don't have to learn a bunch of them or write a bunch of them, the more of them you see, the better you'll be at recognizing what's actually going on there. So that's dynamic programming, upcoming lecture. Backtracking and branch and bound both have upcoming lecture coverage as well. So we'll touch on them today to make sure that you have an outline of what they are, and then we'll go into more depth on each of them later. We're putting them in pairs because they have some sort of relationships here. Brute force and greedy are paired together because they're both basically simple. That's why we'll talk about them that way. What is brute force? Something that solves a problem in the most simple or direct way. Brute, the hulking brute, something that's not too smart. And that's what brute force algorithms are, is they're not too smart. They essentially try everything. Things that are good, things that are not complete, things that are bad, things that are even more than complete. They try everything because they don't really have the ability to distinguish what is something that should be tried or not. It just tries everything. That does, however, make it fairly easy to implement. You can usually just loop over all of the things or find a double loop to loop over all the things, or whatever it takes to throw everything at there. So you often end up doing more work than you need to, and it doesn't usually end up very efficient. However, it will always find an optimal solution. When I say optimal solution, I mean a solution that has the best possible values. And that is because yes, audio has returned. Okay. It was Discord's fault. Discord saw my microphone and decided, hey, we're going to use that microphone and cut you all off. So I got some backtracking to do, apparently, because I got some lecture that I missed. So let me pop over to the chat. Nice. So when did I lose this? Oh, crumbs. Yeah, there's just not enough real estate. I'm watching the feed over here, the lecture over there, the slides there. That's why somebody's supposed to be on this. Who's on this? Nobody's on this. Got me out here soloing. All right. Let's see if I can't slide this a little bit this way. And there I can see a little bit of the chat window. Okay, anybody want to give me a slide number where this went dead? Cons of brute force. Perfect. That I can manage. Backing up there. Half a slide. Okay, I see the green. It's flashing. There's the green over there. There's a chat over there. There's the slides up here. The camera here. All right. So we were talking about brute force algorithms. Brute force algorithms, because they aren't smart about the way that they do things, they often end up doing more work than is necessary. And that's pretty obvious because they try everything. So if I think of a simple example that I'm going to show up in just a minute with counting change, brute force is going to look at all possible combination of coins, even many ridiculous combinations. Like you're trying to make 17 cents, how about these 4 quarters? Well, I've got 4 quarters, I got to try it. It's one of my options. You don't like 4 quarters? Well, how about 5 quarters? That's one of my options too. Brute force just says, how about all of these things? So it does a lot more work than necessary when you know that once you've gone past the change you're giving, you should stop adding coins. So it doesn't usually give you an efficient solution, but because it tries every possible outcome, it finds all solutions, finds all failures, but it also finds in all of the possible solutions, it's going to find the best solutions as well. If there's multiple optimal solutions, it will find every single one of them. If there's only one optimal solution, it will find that because it finds everything. So you often do more work than necessary, but you can be assured that if you have the time, you will find the ultimate solution, the ultimate optimal solution with brute force. So here's my example, counting change. This is something we used to do back when I was a kid and people used paper money. You give the cashier some paper money and you give them too much money, so then they throw chunks of metal back at you. We call this making change. And the cashier has a drawer full of various denominations, and their goal is to give you back exactly the money that you should have back. Not too much, because that would make their employer upset, and not too little, because that would make their customer upset. Just the right amount, and customers don't like walking around with a whole pocket full of change. They don't need to. So let's try to keep the number of coins given back as low as possible. So we're trying to return the specified sum using the smallest number of coins. Enter brute force. Let's count some change with brute force. If I think of all the subsets of coins to make change, this is what I've got going on. So there's these subsets S and C, right? The subsets are of the coins C to make the change totaling A. Since there are n coins in C, the total number of coins is n, there's 2 to the n possible subsets. And I get that. I get that. Sorry, I caught that minimum wage comment there. When I get that 2 to the n possible subsets, it's because each coin is either in or out. So for each coin, there's 2 choices. 2 coins, 2 choices, times 2 choices. 3 coins, 2 choices, times 2 choices, times 2 choices, times 2 choices, times 2 choices. So that's where we get this really large number. If I just have 10 coins, there's 1,024 different ways that I can look at different combinations of those coins, different subsets. The one subset, which is all of them no, there's no change coming back to you. The other subset, which is all yes, here's all of my coins. I hope that's your change. There's a lot of them in there that brute force would check. So one of the things that we have to do is check to see if this subset that I have, this collection of trues and falses, does that even equal A? Because if it doesn't equal A, that is not a feasible solution. If it's more than A, I've given back too much. If it's not enough, I haven't given back enough. So that is not good. And I can do this in linear time, right? I've got these n coins. I just look at what have I said yes to, and as I see each one of those, I add, and then I say, oh, does that total A? Then that's a feasible solution. How about the minimization step here? This is what we call our objective function. We're trying to minimize this whole thing here. I want to see how many coins are there. Well, it turns out I can do that in my same linear loop. As I pass, I'm like, yes, no, 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 yes, 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 no, 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 no. I can count all my yeses in that single pass and say, well, that's the total number of coins that I have. So I have to look at all these 2 to the n subsets, and each time through I have to do linear work to see if that even totals up to A. And during that linear work, I can do some additional linear work to say how many coins is that as well. So here's an example, and this is a reduced example because this is not going to fit on one slide. All I have here is actual combinations that add up to 30 cents. Keep in mind that brute force gets all of the combinations. So it's got the ones that add up to 1 cent. Is this your change? No. 2 cents? How about that? How about 3 cents? No. It keeps going. It gets all of those. 50 cents, 80 cents, $2. It depends on how many coins you have. We're trying to get to exactly 30 cents, and all I have space on the slide here is to show you the ways that I can actually get to 30 cents. So you can see here, one way to do it is just with 30 pennies. 30 pennies gets me 30 cents. That's great. Another way to do it here in the middle, I got a dime, nickel, and 5 pennies. gets me there in 17 coins. Sure, 17 coins will give me 30 cents, but that's not how I want to walk around. I'd much rather walk around with my optimal down here. My optimal has just the 2 coins, quarter, nickel, 30 cents. So brute force will find all of these and many, many more, but at the very least it's going to find these. This is my feasible solution set. All of these things actually add up to 30 cents. How's my complexity look on this? Well, I got this big omega of n times 2 to the n, right? N times 2 to the n because I've got to do linear work for each one of my 2 to the n subsets. So I've got those 2 to the n subsets, I do linear work on it. In the best case, I end up with this big omega of n to the 2n. In the worst case, it's the big O of n to the 2n. So we're pretty much n times 2 to the n. Brute force counting change is not efficient. If I've got 10 coins in my drawer, like I said, I've got to try 1,024 different combinations. If I've got 100 coins, I've got 2 to the 100, and that's almost unfathomable in terms of numbers. So you wouldn't want to brute force it. All right, let's look at greedy algorithms. I said brute force were simple because they just tried everything. Greedy is simple in a different way. Greedy is going to make a sequence of decisions without ever looking back. It's not introspective at all, and it doesn't look very far forward either. It doesn't do any long-range planning. It just says, I'm greedy. I want the best you got, and I want it right now. So it makes these what we call locally optimal decisions, right? The locally optimal decisions are the ones that say, this is the best I can have right now, that's what I'm going to take. I'm not going to worry about the fact that this best that I have right now, so like say there's cake on the table. Greedy person is going to take the biggest piece of cake. That's obvious. We've all been there. I'm not proud. But if I said, if you take this small piece of cake today instead of that big one, I will give you a whole cake tomorrow, a greedy algorithm would fail. It would say, nope, I still want that big piece of cake. Just give me the big piece of cake. We'll worry about tomorrow's cake tomorrow. Well, yesterday's cake made us sick. We won't worry about that either. Right now, I want big cake and I want it now. So a greedy algorithm just takes this locally optimal decision. So here's my choices, choice A, choice B, choice C, choice D. Give me the one that gives me the most or the least, whatever you're trying to do as you're optimizing. It takes the thing that's most important. So if the biggest item is most important, it takes that. If the smallest item is most important, it takes that. We always have the ability to turn our optimizations up and down. So it takes these locally optimal decisions and just strings a bunch of them together. Sometimes you get a globally optimal solution. Sometimes you don't. So what a globally optimal solution is one that's actually a full solution that's optimal, that's made up of all of these small steps. If that's in the end optimal, that's a globally optimal solution. So we have to prove that our greedy algorithm is globally optimal. It's usually pretty easy to figure out what the steps in a greedy algorithm is. You look at what's available and say, what's going to be the most helpful right now? So it's not too hard to find those. They end up running a lot faster generally than brute force because they take some shortcuts. The cons, however, is they don't always lead to a correct or optimal solution. Sometimes being greedy is not going to get you everything that you need. I'm not trying to write parables here. So let's go back to counting change. We're going to go from the largest to the smallest denomination because I'm trying to give change back. I'm trying to do this in as few coins as possible. I want to give back as much as possible with every step. So that's my greedy. My greed is here, take it, take it. So we'll start at the largest denomination and go from the largest to the smallest. And then every time I can give you a coin, I can subtract how much I owe you. And then I try to find the next largest coin I can give you. This turns out to be the way that we actually do make change. We have our drawers all set up. If I got enough to give you a quarter, I give you a quarter. If I don't have enough, then I go to the dimes. If I got enough to give you a dime, I give you a dime. If I don't have enough, then I go to the nickels and blah, blah, blah. So this is how we make change. If my money is already sorted by value, now the algorithm is pretty fast. If it's already sorted by value, I start at the largest coin. It's either in or it's out, and I move to the next coin. It's either in or it's out, in or 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 out. And when I get done, that's it. So I can do this in linear time, which is far quicker than n times 2 to the n. So we can see how, even though greedy is simple, brute force is simple, greedy is much faster. There's the caveat, though. We'll get back to it. So here, as we're trying to take my 30, and I'm making these 30 cents change with the American coins here, quarter for 25, dime for 10, nickel for 5, penny for 1. That's how I'm going to make change. My greedy algorithm always says if I owe you more than 25 cents, I'm giving you a quarter first. That's step one. I'll give quarters as long as possible until I can't give any more quarters without giving you too much money. Excuse me. And I'll give dimes. That's not going to work. Whew. Pick dimes if possible, pick nickels if possible, pick pennies if possible. Like I said, this is how it really works. So this is something that you should understand. This is a greedy algorithm. You were taught when you were very small, when you first started learning how to handle money, you were taught this particular greedy algorithm. So using this, I get one solution, and it's actually optimal in this case, which is great. I do the 25, can't give you any more 10s, I give you the 5, and then I'm done. So greedy finds one solution to this problem, and it's the optimal one. That's great. Does it always work, though? In this case, I'm going to ask you this question here. Can you devise a set of coins for which greedy does not yield an optimal solution for some amount? You can pick the amount you want, or you can pick the denominations of the coins. Either way, how can you do it? And this slide did not get an answer delayed, so there's the question and the answer all at the same time. No way that there was that much math going into the money design, you don't think? Wow. Well, look at how our money goes. At least in the US, we got $1 bills, 2s, 5s, 1s, 2s, 5s, 1s, 2s, 5s. Then we got 10s, 20s, 50s, hundreds, and there's banks that trade $500 notes, but they aren't in public circulation. But all of the money goes 1, 2, 5 for the most part, because it does help get down there pretty quickly. Even down at the coin level, we got 1, 5, 10. We don't have 2-cent coins, but 1, 5, 10. So that works out fairly well. The 25 is an oddball in there, but it does speed things up. So I think money, if you look at money around the world, it does this sort of 1, 2, 5, 10 thing for the most part. One time in high school, I did something that was finding the optimal way to do money. I think it has something to do with 3-cent coins or $3 bills, because they're actually more efficient than $2 bills. But you can play around with these numbers all on your own. But here's the answer to this one, right after the question. If I'm trying to make 30 cents and I've got pennies, dimes, and quarters, no nickels now, what happens when I go greedy? My greedy says, let me take the quarters first. Now I only owe you 5 cents. Can I give you dimes? Nope, that's too much. Okay, let me give you 5 pennies then, and there's your change. Quarter, penny, 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 penny. 6 coins. Where if I wasn't so greedy, I could have just said, well, I'll just leave that quarter for somebody else who needs more change. I can just give you some dimes. Dime, dime, dime. There's 30 cents in 3 coins. So that's one that doesn't work. So there we've got just a shortage of coin. In the past, people have chosen different denominations. So for instance, what if I wanted to make 21 cents change and I only had 7-cent coins and 5-cent coins, and there's different things that you can do, but you can see that given a particular input, this greedy algorithm doesn't always work. And I think that is why the denominations are chosen the way that they are, because a greedy algorithm like this is easy enough to teach even to, as somebody mentioned earlier, the minimum wage cashiers can even do a greedy algorithm, right? So that's with apologies to all of us, you included, that have worked minimum wage cashier jobs. Been there, done that. So that's an easy enough algorithm to teach to somebody, so you're much more likely to have your store end up with the right amount of money if your employees can apply this algorithm. So it does work with the money that we have. However, you've all been to a store too and they're like, we're out of fives. Anybody can give us fives, we would love that. And when they don't have fives, what do? They give you a 10 and then 7 ones and say, here's your change, right? So that's a situation where the greedy algorithm isn't the greatest when we've got some holes in our denominations. So greedy algorithms have this thing, the greedy choice principle, and we'll talk about that in a second. But if I knocked out these nickels, you see here that I don't get a good solution. I get 5 coins or 6 coins coming back when really the answer should be up here, this 3 coins, which is just 3 dimes. All right, let's pick a new problem. We'll come back to coins in a bit. We'll come back to greedy in a bit. But we're going to do sorting. We've already done sorting, so hopefully you understand that one as well. It's always good to talk about things you understand as we're adding new concepts. Sorting. The precondition is I've got a random array of integers called int, my array, right? And the post condition, what I'm looking for is for all I less than n minus 1, so all coins but the last one, or all indices but the last one, I want to have this post condition such that what's in my array at I is less than or equal to what's in my array at I plus 1. That's what I would call sorted. So there's my official definition of precondition, postcondition. This is what sorting is. By brute force, what do? I generate all the possible permutations. I put every digit in every possible location with every other digit in every possible location. N factorial different ways. That's not so great. Every time I've got a permutation, I end up doing a linear amount of work just to check to see if they're actually in order. This one we like to call monkey sort. So if you've ever seen monkey sort, you can look that up. This is how it works. I got a deck of cards. They're all mixed up. I give them to the monkey. Say, monkey, sort these cards. What does the monkey do? Throws them up in the air. Picks them up in the pile and hands them back to you. Right? Not sorted? Okay, you give them back to the monkey. That's monkey sort. So monkey sort is very inefficient. We do these n factorial throws into the air. That's if we don't ever have the same stack more than once. So let's just imagine this is an ideal monkey. Always gives us these n factorial different ways that I can put these cards in order, and then it's my job to go through all n of them to see if they actually are in order. That's very inefficient, right? We look at something that's n for the check times n factorial for the options in brute force. In greedy, if I find the smallest item and move it to the first location, I can look through all n of my items, find the smallest, and move it. Great. Then I find the next smallest item, move it to the second location, find the next smallest item, move it to the third location, and dot, 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 dot. What sort is that? That's selection sort, isn't it? Find the smallest, put it in place, find the next smallest, and go on. Selection sort is a greedy algorithm. Every time I've got a step to make, I'm going to put one thing into position that I know that I know is in position. That's what greedy is. I can put this one thing in position, and all I'm worried about is putting this one thing where it belongs. I might have something that's really close to where it belongs. So like if I've got 1, 3, 7, blah, 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 2, I'll put this 2 where the 3 is and put the 3 way back at the end of the line. Greedy don't care. Greedy's like, I got 1 and 2. Who cares about 3? We'll get to 3 later. That's greedy. But it still ends up with something that's n squared, which is much better than n times n factorial. All apologies to the monkeys. How about mountain climbing? Mountain climbing. We're trying to get to the highest point on Earth. That sounds like a nice bucket list goal there. If I were to do this brute force, maybe I would lay out a grid of these 1 meter by 1 meter sections. And then if I stand in every one of those sections, you can bet that I made it to the top of the mountain. I got a lot of mountain climbing to do to get there, but you would actually be at the top of the mountain at some point. You lay out this grid and then you visit all the locations. The highest place that I ever was, call that the top. In greedy, I say, well, that's a little ridiculous because I was up here and I had another place to visit and I went down there to do it. That's kind of dumb. I'm trying to get to the top. So greedy just says, well, wherever I'm going, I'm going to go up. If I can take any steps that will take me up, I will take them. I might take some horizontal steps. Those don't really count, right? If I have nowhere to go but level, then I'll go level. But I'm going to go towards the place that's going to let me climb up. So if I'm always increasing my altitude, I must be getting higher, right? You do that until I can no longer get any higher. But what happens? If you've ever seen a mountain, you know that they aren't just, that's a pyramid, right? There's all kind of crags and small peaks, these sub maximums, right? So these local maximums, if you get caught on the wrong path, you could increase until you got to a local maximum, and then you'd be on top of this peak, but not on top of this peak. So the only way for greedy to get from the top of this peak to that peak is to go down again and get to a different place to come up. And greedy won't do that. So this is another example of a greedy algorithm that can work depending on where you start, but it can also get trapped. So it's not guaranteed to always give you a globally optimal solution. How do we prove this? This is the tough part. Proving this greedy optimality. We need to have an optimal substructure, right? And what that is if I can build an optimal solution by taking some action and adding that to an optimal solution for the rest of the problem. If I can take one step and add it to an optimal solution for the rest of it, that's the optimal substructure that I'm looking for. If I can't do that, then I can't solve this problem with a greedy algorithm. I also need a greedy choice property that says, how do I have to choose that first action? Well, I have to choose the first action greedy because all my choices are greedy choices. So if I can make any first action choice greedily, and then what remains is something that can be combined as an optimal solution, then I've got something that can be called a globally optimal greedy solution. I get to, I keep applying this recursively. So this is like I said in mountain climbing. If my next step takes me up a sub-peak, then what remains is not an optimal solution because I'll have to go down to get up there. So that's one. If we were in a situation when we're sorting, and you say, well, if I put this item into place, it's going to permanently prevent me from sorting the rest of the list, then I can say, well, you can't sort that with a greedy sort. We said selection sort's greedy. Those of you that were thinking about it will have noticed that bubble sort's greedy too. I've just looked at these two items. If one of them's out of place, I'm swapping them. That's what bubble sort does. In pairs, I'll just swap these two. And that gets me something better. That gets me closer to sorted. It removes an inversion, and I'm good with that. Anytime I can remove an inversion, greedy's happy. How about insertion sort? Also greedy. Those three elementary sorts plus monkey sort. Monkey sort's not greedy. Those three elementary sorts are all greedy. And they all end up n squared, and that's why they're sort of stay in the elementary bag. But they are also all optimal in terms of their greediness, in the sense that when I select some item and put it at the beginning for selection sort, it doesn't prevent me from later being able to add that to an optimal solution for the rest of the items, which is good. Same thing with bubble sort. If I was to ever bubble two items and once I switched these two, there was a broken section of this array that could never be sorted, then a bubble sort wouldn't work. But we know that that's not the case. Every time I do a bubble sort swap, I can still do some other bubble sort swaps to fix the rest of the things. So that's where greedy optimality is. We're looking for this optimal substructure. If I can always take some action and get an optimal solution to the rest of this and add it together, then that's my optimal substructure. So here's my summary. Brute force solves it in a simple way, generates the entire solution set, picks the best. Usually is going to give typically poor performance, but it will always find the optimal solution because it finds every solution. That's important to remember about brute force. It will always find the optimal solution. if you have the time. Greedy, make these locally optimal decisions. Don't look back and say, well, that was a bad thing. I can fix that by doing something less than optimal right now. And don't look too far forward. If I jump up too high here, I'm going to get stuck. But if I walk around there a little bit lower, I can get higher. Greedy doesn't plan like that. So we often get optimal solutions here. Sometimes we don't, though. And they usually have better efficiency than brute force, which is great. But it always depends upon this greedy choice property that says these global optimums have to be found by a series of local optimum choices. All right? So that's brute force and greedy, our first pair. They're simple, and that's what relates them. Up next, we're going to talk about problems that have subproblems that look like the original problem, only smaller. That's where divide and conquer comes in. That's where dynamic programming comes in. In divide and conquer algorithms, we take a problem solution and cut it into two or more smaller problems, preferably of equal size. That's good. This makes our solutions often recursive because you're like, here's this problem, how can you solve it? Well, if you just make it a little smaller, I will solve that. Well, how will you solve that? I will make it smaller, and then I will solve that. So this is recursion, often happens in divide and conquer algorithms. They often end up then including this log n in its complexity. Why is that? Because I'm cutting it into multiple parts here. This dividing it into 2 is going to give me something that's log base 2. If I were to divide it into 3 parts, I'd get something that was log base 3. If I divide it into 4 parts, I'd get something that was log base 4, and so on. As long as I'm cutting it in, as long as I'm reducing the number of things when I cut it down. Right? Even if I'm doing this reducing by a 1.5 instead of a 2, that still is a reduction. I'd be log base 1.5, and we just consider all of those things big O logarithmic. But that's what's going on in a divide and conquer. The pros of divide and conquer, of course, are they're fairly efficient. Think of some of the ones that we do, right? We do binary search. That's a divide and conquer. I look here in the middle. Where's my answer? It's either over there or over here. So once I found this spot, I can throw these half away and then just expand this and work on it. So that's what divide and conquer does. Oftentimes we have recursion involved. So this is the so-called elegance of recursion, because sometimes recursion looks really elegant in code, but it doesn't make it necessarily efficient. So that's where the elegance is in quotes there. The cons are, of course, when I do recursive calls, most of the time I end up getting down to a lot of small subcalls. If you think about the way that quicksort works, finds a pivot, then sorts this part and this part, finds a pivot, sorts this part. It gets down to a bunch of things where it says, well, this is a list of size 0 or size 1, now we can stop. But it makes a quicksort call on a range that's got 1 item in it or 0 items in it. So we end up with a lot of those because that's the bottom of our search tree there. So we end up with a lot of recursive calls, so that can be a con. Also, sometimes it depends upon the initial state of how I have my data. So for instance, I can't do a binary search if my data is unsorted. So divide and conquer won't work that way. So there is some setup that's required in every particular application of a divide and conquer algorithm. Closely related to divide and conquer is combine and conquer. And this is where we start with the smallest subdomain, and then we combine them to get bigger and bigger partial solutions until we've got everything one big thing. So we talked about that when we talked about n sets of size 1 as we combine to get to one set of size n. So usually when we do this, we think of divide and conquer and combine and conquer as very similar. If you start looking into the literature some, you might notice that divide and conquer is written up not as D and C, it's written up as D and Q. I like the middle letter of conquer there. D and Q, that is top down. We take this big thing and cut it in half and cut it in halves and cut it in halves and cut it. Right? Combine and conquer starts at the bottom, these small things, and puts them together. And so those two approaches are synonymous. Divide and conquer with top down, combine and conquer with bottom up. All right? Some example algorithms, of course, I already mentioned binary search. That's how we do with cutting things in half. We talked about quick sort already as well. Those are both divide and conquer algorithms. You find some place and divide the work into smaller places, smaller sections of work that looks like dissimilar. I had to sort all of this, and then once I cut it into 2 portions, all I have to do is sort the 2 portions and I'll be in great shape. Combine and conquer, of course, is another sort here that the quintessential combine and conquer algorithm is merge sort. It helps us that way. Let's talk about dynamic programming now. Staff favorite, remember. The way that this happens is partial solutions get stored. So you have to store some answers that you calculated, and then when the smaller instances are all stored, when you need that to calculate something bigger, instead of doing the work to calculate the smaller one over and over again, you just look it up. So in the end, we can do dynamic programming top down and bottom up. No matter what though, we're still always going to solve the small instance first, because that's the only way we can do it. We can't solve a bigger instance and then say, well, from this I can decide that the smaller instance works like this. You have to solve the small one first. So if I'm going bottom up, that's really obvious because I'm looping from small all the way up to big. When I'm going from top down though, I end up making these recursive calls, and this calls itself again with a smaller value, smaller value, smaller value, smaller value, base case. Now we got a solution. Return bigger, return bigger, return bigger, return bigger, answer. So we always end up solving these small instances first, and then we store the results, look them up when we need them. The pros are, this is wicked fast. You can get some really, really bad algorithms. So you can take something that's exponential and turn that into a polynomial, and that's great. That's really nice. The con is, of course, just getting it to work. It's really hard to grasp. The first 3 times you learn dynamic programming, it really can be challenging. Really. So you're going to think you got this. And then you walk away from the lecture, yeah, I got this. It made sense. Finally, it clicked. Then you have to write one. And you're going to go back to doing some head scratching and say, I don't understand that at all. You go back and have somebody explain it to you again. You're like, oh, yeah, I get it now. Okay, yeah, I just missed it. Good, I got this now. And then you go to another problem that's a little bit different. Head scratching continues. Go learn it a 3rd time, maybe more for you, maybe less if you're lucky. It was at least 3 times for me though. So don't be too afraid of dynamic programming seeming rough. We'll talk about some of the ways in the DP lecture that you can work your way into DP solutions. So it is pretty difficult to grasp it. Once you see it, you'll appreciate it, but it's often hard to generate it. Here's our first example, and this is a real simple example. It's Fibonacci numbers. And we use this as a simple example because most people understand Fibonacci numbers. I would probably not in the real world use dynamic programming on Fibonacci, but it's easy enough to explain here. So here's my Fibonacci numbers. You know that I can combine any 2 to make the next one. I got my base case. Base case is, excuse me. Base case Fibonacci 0 is 0, Fibonacci 1 is 1. Every Fibonacci number after that is the combination of the 2 numbers previous. So f of n is equal to f of n minus 1 plus f of n minus 2. Try Fib 50. If you do it that way, you'll start to see some pattern there. Fib 50 is just Fib 49 plus Fib 48. Great. Fib 49 is Fib 48 plus Fib 47. And since Fib 48 is Fib 47 plus Fib 46, I'm starting to write something out here, but look at this last line I've got. And that's just getting down 2 levels, right? 3 levels. I got Fib 47 plus Fib 46 plus Fib 46 plus Fib 45 plus Fib 46. So if Fib 46 is expensive to calculate, I will have calculated it 3 times. And it turns out Fib 46 is pretty expensive. because it's got a whole bunch of calls of fib 45 and 44 and 43 and so on. So you can also see multiple calls of fib 45 here. I've got 3 calls of fib 45 and so on. So Fibonacci, doing it in this very elegant recursive way, f of n, just return f of n minus 1 plus f of n minus 2. You can write a recursive Fibonacci solution in just a small number of lines, but it ends up being terribly inefficient. We'll talk more about it when we get into talking about DP. But as we take a summary of these two families, divide and conquer and dynamic programming, their relationship is they both take a problem and solve it by solving smaller versions of that problem. So if I can take a problem and subdivide it into smaller versions, then I can solve it with one of these two approaches. So for instance, I can't lay carpet in a bedroom by saying, well, what if I just lay carpet in this half of the bedroom? And what if I just lay carpet in this half of the bedroom? That's not a way that I can solve that problem. That's not a problem that I would easily solve with divide and conquer or dynamic programming. I have to be able to take these smaller problems. And in divide and conquer, it's important that my subspaces or my subproblems are independent. Independence, like when I talk about binary search, I cut this in the middle. The item that I'm looking for is either over here or it's over there. It can't be in both. That's the independence of those two subproblems. If I solve the problem within those subspaces, I end up with a solution. This works out most efficiently when my subspaces divide evenly. That gives me that log base 2 that's really efficient there. Dynamic programming also needs these problems that are similar to the main problem, but they have to be overlapping. They have to have something like that Fibonacci, where Fibonacci of 45 needs Fibonacci of 44 and 43, but Fibonacci of 46 needs 45 and 44 as well. So Fibonacci 44 belongs to the solution for Fibonacci 45, and it also belongs to the solution of Fibonacci 46. So those things are not independent. I can't say, well, I'll just chop off this 44 and it'll only be used over here. It needs to be used in both sides. So I have to have these overlapping subproblems, or subspaces they're called. And I can do this when I've got partial solutions to these problems that I would then use multiple times later. I save some information there, and then it saves me time later. Oftentimes we end up looking nearby for these previously calculated values. So if I've got some table where I'm storing my results, if I'm looking for the answer to what's in, cell 46 for my 46 Fibonacci number, I can look nearby that to see what's in 46, what's in 45, and what's in 44. That's how that works. We'll go into it more. Just for now, know that you've got a high-level understanding of what DP is that it's a problem that can be divided into smaller versions of itself, just like divide and conquer, but we've got some overlapping with DP and independence with divide and conquer. All right, last set here, backtracking and branch and bound. These are similar. One actually encompasses the other in our basic form. So backtracking is a way to solve constraints, and branch and bound is a way to optimize a constraint solving problem. So we can apply backtracking principles within branch and bound. That's why they're related. To get to the solutions, let's talk about the problems. Constraint satisfaction problems is where we start. One really common popular constraint satisfaction problem, how about Sudoku? This is a number puzzle where you've got to put numbers in this 9x9 grid, and every row has to have a 1 through 9. Every column has to have a 1 through 9. Every row has to have a 1 through 9. And then there's these other boxes in there, and they all have to have a 1 through 9 in there. Those are constraints. I can't have more than 1, 2 in the first column. I can't have 3 4s in any row. That is a constraint. So the question is, can I fill out the puzzle without violating any constraints? Usually we want to find one of those solutions. So if yes, how do we do that? That's pretty important when I need a specific solution. Though sometimes it's good enough to know whether or not a solution exists. Sometimes it's true that you may have more than one solution given the problem. The way that Sudoku puzzles are designed, there's only one solution for that particular puzzle. But there are other problems that might have multiple solutions that you can think of them as constraint satisfaction problems. Some examples of them are, of course, sorting. That's a constraint satisfaction problem. I don't want any item here to be greater than an item that follows it. That's a constraint satisfaction. Getting out of a maze. I can't go anywhere where there's a line. I have to stay within these, where there's a wall, I have to stay within the path. A spanning tree. Is there a way to connect all of these items such that nothing is left out? That's a spanning tree. Now, if I wanted to optimize those things, I have to first satisfy all the constraints. If I can satisfy the constraints, then I'm trying to minimize some objective function that says, how do I add up these things? So some examples are, of course, giving change. We just talked about that. That's an optimization because there's many ways I can give you change, but the one that people appreciate the most is the one with the least amount of change. An MST, which is a spanning tree from our constraint satisfaction problem, but one that's the least weight, that minimization step, the M of the MST, takes that from a constraint satisfaction problem and pushes it to an optimization problem. When I've got constraint satisfaction problems, usually once I find a solution, that's good enough because I was just trying to see, is there a way to do this? Sometimes I might want to print them all, but one is often enough. When I'm doing optimizations, however, I can't stop early because who knows? I just found a great solution. What's to say that there's not a better one if I do some more investigation? So you get this set of feasibility or feasible solutions, this possible solution set. And depending on how you implement your solution, sometimes you may have to remember all of those, but generally it's good enough to say, I've got this thing that's feasible, and I'm going to remember that because I think it's the best until I see something better. As soon as I see something better, throw that away. Now I've got a better one. So you can sort of develop a set of possible solutions. You may store all of them, you may not. It might depend structurally on how you do this. If you're doing some recursion, you might have them implicitly stored in your call stack. But you need the best solution. You can't find it until you've gotten through all of them. And that's what you end up with at the end. So now that we've got those problem types defined, I can say that constraint satisfaction problems can be solved with backtracking algorithms. And optimization problems can be solved with branch and bound algorithms. Those are things that are optional. What that means is for any one of these, for any particular problem, you might have something that is another much more elegant solution. But if you can't come up with that much more elegant solution, you can always fall back on just doing a backtracking algorithm for constraint satisfaction. So here's my definition of backtracking algorithms. And you listen to it, you're going to hear something that's going to raise some red flags. The definition of my backtracking algorithm is something that can systematically consider all possible outcomes of each decision, but then prune searches that don't satisfy one or more constraints. So systematically consider all possible outcomes. Sounds like brute force. And in many ways, it is like brute force. It is asymptotically similar to brute force because we do have to systematically consider all possible outcomes. However, it's that but that makes a difference. But we can prune the searches that don't satisfy constraints. And what I mean by prune is chop off. Don't continue to go down that way. So you can think of pruning just like you prune a tree. You remove some branches that aren't going to be attractive or healthy or something like that. So you can think of backtracking as this depth-first search because it's trying to get through all the decisions that it needs to make to the bottom. However, when we run into some decision that violates a constraint, we don't have to make any more decisions below that because we've already violated one constraint. So imagine that you are trying to escape from a death maze. What's a death maze? It's a maze that you're walking in and there's things in there that will kill you. Fire pits, raging animals, electricity, you name it. So you're going through this death maze and you're told by your extremely pleasant captors that you can get out of this death maze by making 10 left, right, center. Well, if you go left first and then you go left again and you die, nobody cares about the remaining 8 decisions. So you say, well, I turned left once and it looked like certain death to the left again, so I can prune that and I don't have to make those decisions after that. So that's what the pruning is. I'm trying to get to a combination of decisions that will get me out. Or as I'm making some decision, I start at the top of my decision tree and get to the bottom. And that's what the depth first is. When I get to the bottom, I've got a solution. I've made decision 1, followed by decision 2, decision 3, dead end. So make a new decision 2, let's go over this way, and so on. That's how backtracking works. The pros are, it does eliminate the exhaustive search. Even though it says systematically consider, that pruning says, well, this isn't worth considering. So you don't have to do the work on it and you'll still have the correct answer. The cons are, we still generally end up with some fairly large search spaces, but it can be pretty efficient when we see backtracking algorithms work. Let's try some applied backtracking. Let's go into forecoloring. Let's graph color. And what a graph coloring is you assign a color to these vertices. Each vertex gets its own color. And then you say that any 2 adjacent vertexes can't have the same color. That's it. So given a graph, the question is it forecolorable? Let's do this with backtracking. And this graph coloring is also how you end up with something like this. This map has been colored, and if you look closely, it's got 4 colors: red, purple, green, and yellow, but no 2 neighboring states are the same color. So you can always tell where a state's border is because it changes color to the state next to it. And if you look closely, even in the small East Coast area over there, there's still no 2 states that are touching each other that are the same color. How does that work? This is just a graph. We call it a map. It's a cartographic map. But if I represent each one of these states as a vertex, California is a vertex, Oregon is a vertex, Nevada is a vertex. And then if 2 states have a border between them, I just draw an edge between those 2 vertices. So there would be an edge that connects the Nevada vertex to the California vertex. There's an edge that connects the California vertex to the Oregon vertex, and Oregon to Nevada. But there are no edges between the California vertex and the Idaho vertex. Note, both of these are colored green in this particular instance, but that's not important. It's just happens to be a side effect here. So if I can take this whole map, and instead of looking at it 2D like humans want to, I can just simplify this like graphs allow me to do, and turn this into 50 vertices and some collection of edges. That's really what I'm trying to do. If I can then color that graph, I can step back and apply some colors to my map as well. So cartographic maps can be drawn as a planar graph, just as I mentioned. Each state or location is a vertex, each border is an edge. A planar graph is one where I can draw the graph and have none of my edges cross. If there's an intersection in the middle, that's fine. But if I've got 2 edges that connect 2 points, or 2 edges that cross each other, and there's only 4 points involved, then this is not a planar graph. You can go try that. Try to draw some physical space on a map that you couldn't represent with a planar graph. You just can't do it. So let's take this southeast corner, the United States. I've got Mississippi, Tennessee, the Carolinas, Georgia, Alabama, and Florida here. And I'm just going to try to use these 4 colors, red, blue, green, and orange, and then work my way through trying to color this to give you an idea of how backtracking works. So to start with, I'm going to pick a state. Let's start Mississippi. And I'm going to start with my first color, red as well, and just try to apply this. And you can see my borders, Mississippi borders Tennessee and Alabama, and so on. So I'm just going to work my way through the colors, red, blue, green, orange, red, blue, green, orange, and try to keep placing those again. So as I move clockwise around this, I'll see my next state up is Tennessee. I'm going to color that blue. No constraints violated so far. I only have two colors, or 2 states colored in 4 colors, so I can't possibly have a problem just yet if I'm smart. So now I've colored North Carolina green. Mississippi and Tennessee have a border. Tennessee and North Carolina have a border, so it's important that they all have different colors there. Moving around, I can see that South Carolina gets colored orange with my current algorithm. Going clockwise, no problems there. Next up is Georgia. If I color Georgia red, how does that look? There's no edges between Georgia and Mississippi, my 2 red states. Next up, I'll add Florida in there at blue. That's good. I'm just working my way clockwise around the states. And when it comes time to throw in green for Alabama, I've got a full-on conversion. So I pulled that off with no backtracking. That one worked out just great. Let's up the difficulty level then. Can I do it with just 3 colors? It's harder to have no adjacent colors if there are fewer colors. So starting at Mississippi, I'll do the same thing. I'll color it red. I'll color Tennessee blue, and then North Carolina green. Up next, South Carolina, of course, red. And since the 2020 election, now we can color Georgia blue, right? Wah, wah. Look at where Georgia is. I've sort of highlighted it with a ring around it there. But Georgia, if you look, is adjacent to a red state. It's adjacent to a blue state. It's even adjacent to a green state. And since those are my only 3 colors, if I try to apply any of those colors to Georgia, I've violated a constraint. So this is a constraint violation no matter how I try it. And depending on how you write your algorithm, you may try it at red, see that it fails, try it at blue, see that it fails, try it at green, see that it fails, and say, well, there's nothing I can do to Georgia. I must have to backtrack, and let's make a new decision. Right? A new previous decision says, well, the last thing I did before I was unable to work Georgia was I colored South Carolina red. Let's back up and try some other color there, like blue. Great, now South Carolina's blue. What happens with Georgia? Georgia is still adjacent to a blue state and a green state, but is no longer adjacent to a red state, so I can do that. How about Florida? I can continue around the circle. Red goes to blue, blue goes in there, and then what about Alabama? You see Alabama is adjacent to 4 different states, but they're all red or blue, so I can pretty easily make Alabama green. And there is my 3 coloring here with a real brief look at where my backtrack happened, right? Once I've got to something that I can't fix for Georgia, I have to back up and make another decision, a previous decision, a different decision at a previous level. So, what is the difference here between enumeration, looking at all the different ways I can do this, to backtracking? In enumeration, it's pretty simple. I just apply everything. At the first vertex, I can consider each one of the 4 colors. This is back to 4 coloring now. Then I go to the second vertex. Consider 4 branches below that, 1 branch for each color. Then I go to the third vertex, 1 branch for each color there. I can keep applying all of these things in there. What happens when I've got backtracking though is I look at 2 vertices that I've just colored. Let's say I've colored 1 and 2. If there's an edge between the 2 of them, then there are a bunch of dead ends that won't lead to a good solution. So if vertex 1 is up here, I've got these 4 colors coming off it, and then vertex 2 is below it. I've got the 4 colors coming off after red, I got 4 colors coming off after blue, I got 4 colors coming off after green, and 4 colors coming off after orange. So each one of those is giving me 16 different branches, 16 different ways that I can choose 2 colors for these 2 vertices. If there's an edge between them, then when I go red at the first decision, I can't go red at the second decision without violating a constraint. If I go blue after the first decision, I can't go blue without violating constraint. I can't go green to green without violating constraint. I can't go orange to orange without violating a constraint. So I end up with, even at this level, I end up with these 4 dead ends out of 16 branches, which is the pruning that I was talking about. I've cut out, these 25%, 1/4 of the possible decisions that I make after that. And that's pretty powerful if you think of the earlier that I prune, the more work I save for myself. Because if I was just to color 4 states, 4 colors, I end up with this first decision with 4 below it, the second decision has 4 below it, the third decision has 4 below it, and then the fourth decision has 4 below it. I end up with 256 leaves of different ways that I could combine these colors for just those 4 things. And a lot of them are constraint violations. When I find out after the first 2 steps that I've cut out 1/4 of what remains, I'll end up with some pretty huge savings there. And we'll talk about this more when we get into the full backtracking branch of my lecture, but I'm dwelling. So backtracking allows me to branch on every possibility. Hey, I could color this state that. I could do this thing. And I maintain these 1 or more partial solutions. As I mentioned, sometimes you do this actually in memory. Sometimes you do it using the call stack if you're doing some recursive stuff. Local variables hold a particular state as you move down. Then if you return back up, you're to a previous state that has a partial solution there. And you check every partial solution to see if it's valid. If a partial solution survives, you keep extending it. But if it violates a constraint, then it makes no sense to try to make more decisions after a violated constraint. They're all just going to be wasted work because it's not going to work. So you backtrack. That's what the backtracking is all about. Why is that better than enumeration? Well, we cut out so much. I saw a show just with those 2 nodes. If I find the first of them are the same 2 colors and they're adjacent, then I can cut out 1/4 of the work. The red, red, blue, blue, green, green, orange, orange combo, I don't have to go any farther below that. That's 25% of what's there. So here is my M coloring algorithm in pseudocode. I've got N nodes, M colors, and then I've got this adjacency matrix that tells me of these N nodes, which ones are next to each other. So in this adjacency matrix, I've got true if there's an edge between I and J, and false otherwise. So the output is going to be all possible colorings. So this one is going to print all the possible colorings. So we may have more than one way to color this map. And this will print them all when I do this. Here's the pseudocode here. M coloring. Breathe it in. Last line of M coloring. It's a call to M coloring. So we have a recursive function. Recursive functions never work without a base case. First thing we got to do is get out before we can recurse. So what stops us? When I is equal to N, when we've done all the deciding, when we've colored all the states, be done. There's my base case. When I'm finished, quit. Otherwise, I've got this thing here says, if I've reached N, I've got to stop. But since I want to see what that coloring is, you see that I've got this print statement that prints all of my coloring. And then it returns. So that's how I get out when I'm done. If I'm not done, what do? I'm trying to extend my solution. So if I'm not done, I, that is my parameter here that I call them coloring with, I is less than N. So if I is less than N, my for loop down here is trying to extend my solution, is trying to make I larger. So that's why you see this call to M coloring with I plus 1 eventually. But what makes these algorithms so hard to track is that it's recursive, and we already have some fundamental challenges as humans thinking recursively. It's recursive, but this recursion is also inside iteration. So that iteration makes it harder to see when you get deep into the recursion, you're still also in the middle of an iteration. So anytime that your recursion fails, you're going to pop back out to somebody else's iteration until that fails, and that pops back out to somebody else's recursion. So the recursion iteration get looped and layered in there together, so make sure that you can track one of these down. But let's see what happens. If my I is not equal to n, I have a partial solution. So what I'm going to try to do is apply one of these m colors to the next location. So I'll say for each one of these colors, 0 through m, try placing that color into this next vertex. If that is promising, what does that mean? That means if when I placed red on this state, it's not next to another red state, then I can extend the solution. But if I place a red state next to a red state, I violated the constraint. That's not promising, so I don't extend the solution. I don't call m coloring with, say, we'll try the state after that. We say, okay, well, if that's not promising, what happens? I fail the if statement. I go back to the top of my for loop. Say, okay, we'll try the next color, red state next to blue state. That's promising. No constraints have been violated. Now let's try to add a third state in there, which is the m coloring at I plus 1 again. So that moves it farther down the line. That's how this works. So eventually I can get to a place where I've got everything colored. Every time I call m coloring, I goes up by 1. Eventually I equals n. I print all of those answers out and I return. If, however, maybe I have something that can't be colored like that. Maybe I can't do it for some particular graph or some particular set of colors. If I can't do it, I is never equal to n. The print never happens. No output happens. You run the function, it returns. So it's only when something works, when I've got something promising, that I extend the solution, and then I can eventually extend the solution far enough to cover the whole problem. All right? That promising function that was in there. Promising is important to all of my backtracking functions, but it's different for every problem solution. In this case, as I'm looking at graph coloring, what does that look like? I just said I'm trying to color vertex I. Let's say I'm trying to color the third vertex. Well, great. All I need to do is go back through all of the other vertices, because I'm sort of coloring these in order. So if I'm coloring the third one, I just have to look at the first and second and see, well, if the first or the second is adjacent to the third and they're the same color, not promising. But if they're neither adjacent nor the same color, we end up returning true, saying, hey, that's a good way to try to color 3. And as we add this in, we keep calling promising every time we color a node, or attempt to color a node. So the promising is key to backtracking, but it is independent for every problem. Every problem domain has its own way to decide, is this partial solution okay? Has this partial solution violated any constraints? Yes or no? That's what's going on there. When is backtracking efficient? Well, backtracking using this pruning does avoid looking at large portions, but it doesn't necessarily change the asymptotic complexity. So if you think, what if I were to prove 99% of the search space? Sounds great, but 0.01 times b to the n is still big O b to the n. So it ends up looking asymptotically not so good, but generally it does end up working quite well. Because when I've got constraint satisfaction problems, I've got a couple of different ways. I've got a lot of constraints, and what that does is the more constraints I have, the more likely I am to violate one, the sooner I am to prune, the less of the total search space I look at. So it works pretty well when I've got highly constrained situation. All of these violations lead to massive pruning. When there's not too many constraints, it's also pretty straightforward as well. As I just run through there without hitting any problems, and I get to the bottom of my search tree, and it works out. So my acceptable solutions end up densely distributed, so it's quite likely that I can find one easy and terminate. So backtracking is fairly efficient quite often. All right, we're summarizing here. It seems like we've missed something. All of branch and bound. All right, so I'm going to sum up branch and bound pretty quickly. As I mentioned, we've got a whole branch and bound lecture. But branch and bound now applies this objective function to a solution. That objective function can tell me this solution is not as good as this solution. This solution has a 5 associated with it. This one has a 95. I'll take the 95 over the 5, or whatever it is. I've got to have some way to evaluate these things objectively. So when I've got that, I can continue to use backtracking. I'm trying to optimize now, but I can continue to use backtracking the way I had before. When something violates a constraint, throw it away. It's a waste of time. But branch and bound says when I can compare one solution to another, that allows me to say, well, this might be a legal solution, but since I'm looking for the best, I want the best. I get to throw things away that look like they're a partial solution that haven't violated any constraints, but it's not going to be an improvement. If I've already got this thing for 40, why would I settle for some solution that looks like it's only going to give me about 30? Say, no, halfway through this 30 solution, I'll throw that away because I'm only looking for something that's better than 40 on my way to this 95. So that is a little opaque, but that's roughly how backtracking works. How branch and bound works. And like I said, we are going to do a whole lecture on branch and bound when we talk about adding in the ability to change what's promising now. Backtracking promising is only things which do not violate constraints. Branch and bound promising is only things which do not violate constraints and look like they're going to give me something better than what I already have. And that's the trick of branch and bound, also known as Project 4, Part C. You'll get there. All right, that's what I got here. Let me peek at the chat here and see if I can't cover anything that needs to be covered right now other than stuff we can hit in the office hours. Previous example, 3 coloring assuming is not 2 colorable. Would a backtracking algorithm come to a conclusion that 2 coloring is impossible? If you're trying to do 2 coloring, then yes, it would figure that out. Backtracking won't give you a 2-colored solution if you're trying to do a 3 coloring. It might, but that would be it would be not something that was planned. It could happen. So yeah, I mean, if you had a particular set where you could go red, blue, red, blue, red, blue, red, blue, red, blue, even though you were trying to 3 color or even 4 coloring, it would be possible to return something that worked like that. So I guess the answer yes. The pseudocode only printed the solution when one was found. How would you modify it to print nope when no solution could be found? That wouldn't be too tough. You kind of set some Boolean outside of the call, right? To say if I've ever found a solution, I can return something there. Otherwise, you would have to do it outside of it, right? Because each call to M coloring is only going to find one particular coloring and print it or not. So it can't be sort of like a nope in the middle because the recursive nature and multiple calls to M coloring would be such that somebody else has to print nope. Does that make sense? Con for DP also be the large space complexity. Yes, that is something that you have to be concerned with DP. Is there enough memory to hold it all? If there's not enough memory, then I can't do it. And that's one of the things why we don't end up using DP for, well, that particular version of DP for when we're doing gen perms in Project 4C, you've got this set of points. And so you don't want to say, well, I've already calculated this before because that ends up being factorial different combination of other points. And so you can't store that much information. So it is a particular type of problem that DP can be used on. All right, that's it roughly here. We're a couple minutes over here, but any of these things that seemed a little opaque to you, as I mentioned, we're going to do a whole lecture on DP. We're going to do a whole thing on backtracking and branch and bound stuff, and you'll get there. All right, let's get some lunch.